Thank you so much for joining us today. My name is Victoria, and I'm a Senior Business Development Coordinator at 2H Offshore. Our webinar today is entitled Optimizing Mooring and Power Cable Design for Deepwater Floating Offshore Wind. Before we get started, I'd like to cover a few important housekeeping items. Firstly, the webinar is being recorded and will be made available to you soon, so please look out for a link to that in your email. Secondly, if you have technical or content-related questions today, please feel free to ask them at any time. You can use the Q&A box that is located on the right-hand side of your screen. At the end of the presentation, we'll go through as many questions as we can, but if you have further questions, feel free to contact our speaker directly after the presentation. So with that, I'm very happy to introduce our speaker today, Yusuf Arakan. Yusuf is a principal engineer at 2H Offshore. He has over 15 years of engineering experience in the design and analysis of various onshore and offshore structures, including hydrodynamics of various floating offshore foundations, mooring systems, power cables, drilling and production risers, and aeroelastic and hydrodynamic coupled analysis of floating offshore wind turbines. So with that, I'm going to pass things over to Yusuf to get us started today.
Thank you, Victoria, for the warm introduction. I am very excited to be here today, speaking on this topic. I hope the information we share today is you will be useful for you all. Today in our webinar, we will talking about the mooring and power cable configurations and challenges and opportunities for deepwater floating offshore wind turbines. In our scope, in our study, there are a few challenges and a few assumptions. For moorings, we adopted using synthetic ropes and minimize the chain usage to lower the cost and weight, and eventually the cost of levelized cost of energy. The chain, when compared to the synthetic ropes, they are per length cost is expensive, and in addition to per length cost, it is the handling offshore time that is a big contributor to the cost. So we with the deep water systems, there is more ropes needed, more mooring lines needed. So we try to eliminate or minimize the chain usage. On deep water floating offshore foundations, there can be big, large footprints as opposed to shallow water floating foundations, and slight changes on the angles, on the mooring hang-off angles, can amplify the footprint on the seabed, and therefore it is more sensitive to mooring hang-off angles. Being in the deep water and having long mooring lines, and we observe large foundation offsets even in the intact condition, and also when a mooring line fails, we observe large offsets, and it can cause potential collision with the neighboring foundations, and also can lead to power cable failures. And the challenges for the power cable, currently all the dynamic power cables for shallow water, the tension requirements wasn't that high, so they have a limited tension capacity. So for deep water, just because of the pure length required all the way to go from the foundation to the seabed, just the weight of the power cable requires high tension capacities on the power cable. That is a big challenge. And on the power cable side, the dynamic cross-section, dynamic portion of the power cable is the expensive bit as opposed to static part, and where deep water and the long dynamic power cable sections are required. And again, as we mentioned, in the deep water, we observe high offset, foundation offset, and the power cable has to stand those foundations offsets. So that's a design challenge. In addition to those challenges, actually, in the deep water, there's also opportunities, especially for the power cable. And in the deep water, there's an opportunity to suspend to power cables between the neighboring floating foundations, where you cannot do that in the shallow water. We are gonna explore all those in a few minutes. Uh, First of all, for our study, we are looking at taut mooring configurations with a 15 megawatt wind turbine generator and a foundation for it, floating foundation for it. And we are going to be looking at the polyester and nylon synthetic ropes, mostly in the mooring line composition. They will take the most of the mooring component. There is some performance differences, mechanical property differences between polyester and nylon, and we'll see that how it affects the mooring design. In our study, we are looking at the 1,000-meter water depth offshore California. The picture on the right shows the coal areas, BOEM's coal areas in offshore California. There are 5 identified so far. We are looking at 50-year extreme events where the turbine is parked. That corresponds to the IEC design note cases 6.1. And wind speed is 38 meter per second at 10 meter above the mean sea level. HS is 12.5 and TP is 20 second. We are targeting to keep our mooring strength utilization to less than 95% according to DMV standard 119. And as a base case, we are looking at the consequence class 1, which means a redundant system and no collision with adjacent structures are expected. This is our base case assumption, and I'll be talking about those consequence classes and redundant and non-redundant system in a few minutes. What is the difference, how it affects our design. Again, we are using a 15 megawatt floating foundation. It is a 3-leg semi-submersible design with steel construction. Taut configuration as seen in the picture. We are looking at 3-leg mooring system. That is minimum number of mooring lines you can have, pretty much. There are 120 degree separation angle. We have a slight small amount of chain at the top and bottom to facilitate the connection to the hull and also to the anchor. Mooring hang-off angle, we are looking at from 30 degrees to 45 degrees. The reason for that, 30 degree, when the mooring hang-off angle starts to get less than 30 degree, the efficiency of the mooring decreases. It becomes more like a TLP design, and you won't get to like the restoring force, lateral restoring force you need from a mooring line. And 45 degree angle, you can see the footprint from fairly to the anchor becomes around 1,000 meter or 1,000 meter water depth. And increasing the hang-off angle more than 45 degree to let's say 60 degree, it will double the footprint angle, footprint range to close to 2,000 meter, around 2,000 meter. Even though it is helpful for the mooring design. With the 60 degree angle, you have you'll get more lateral restoring force with the same mooring tension with 60 degree angles. However, the footprint will be too much, and it may start interfering with other mooring lines from the neighboring foundations. So we try to keep the mooring hang-off angle between 30 and 45 degrees. And we look at different preload levels on the mooring lines from 10 to 30% of the breaking load of the mooring lines. Starting with the polyester configurations, we started with a 2,500 ton polyester rope. The reason we started with 2,500 ton, we knew from our shallow water mooring experience that the limits usually are pushed to the industrial limits, and 2,500 ton is right now the current chain size limit that we will need to chain at the top and bottom. So we pretty much started with the highest chain we can have. The 2,500 ton corresponds about 175 millimeter diameter chain with around 8 to 10 millimeter corrosion included. So we start with 2,500 ton polyester matching the chain, and we start with a normal nominal preload of 20% and hang of angle 30 degree, and utilization is 99%, which is higher than what we want. So we want to lower it. One way to lower it is to reduce the amount of preload. Once you reduce the amount of preload on the mooring line, the utilization goes down to 89%, which is okay. But we know that hang of angle going from 30 degree to 45 degree hang of angle is also going to help us in the design of the mooring. So if we increase the hang of angle to 45 degree, again comparing with the configuration 1 with the same 20% MBL, the utilization on the mooring line goes to 91%. That is about 80% reduction from the configuration number 1, just because of the hang of angle. And if we take advantage of reduced preload and also the increased hang of angle, we can actually reduce the size of the mooring line, the strength requirement for the polyester to 2,000 ton with 10% MBL and 45 degree hang of angle, and we can have a working solution at utilization around 80%. Please keep in mind this is not overly optimized yet, because there can be some project requirements may not be that as stringent, and it might allow more than 45 degree hang of angle, for example. And with that further refinement, we believe we can actually reduce this mooring the polyester strength requirement to maybe 1,500 or 1,750 ton levels. For the nylon, again starting with the same breaking load levels, about 2,500 ton, starting with again 10% preload from the last from the polyester case. You can see the utilization is low at 47%, but the problem is it is too loose, and there is some slacking events, and the whole mooring line, especially towards the bottom, goes into slack mode, which is not we don't want that happening in our mooring lines, and every time there's a wave event. And then this configuration 2, increasing the preload level to get rid of the slacking events, and it helps with the offset as well. With 25% preload, our utilization goes to 67%. So there's still margin in our strength utilization, so we can lower the MBL requirement and use a smaller nylon for our mooring configuration. And going with 1,500 ton nylon, yeah, and looking at the configuration 4 and 3, you can see with a higher hang of angle, 45 degree hang of angle, and 30% MBL, we have about 80% utilization. And similar to what we did for the polyester, and we use a reduced preload and a higher hang of angle, we can actually further reduce the nylon size to 1,000 ton. So with 20% MBL and 45 degree hang of angle, we have around 80% mooring line at around 80% utilization, which is a good margin, and it leaves room for further design consideration sensitivities. So it's a good place to be at for a project. And I'm sure you notice that the polyester strength requirement was 2000 ton, and the nylon strength requirement is only 1000 ton, which is half. And the reason for that is nylon is quite more flexible than polyester, and it's more compliant. And even though it produces larger offsets, it the strength requirement are usually lower than the polyester. Therefore, you will use smaller size chain, smaller size anchor, and it has those advantages over polyester. I like to I like to talk about the mooring redundancy philosophy and turbine spacing in a deep water, how two are related, and how it can affect our design. First of all, I want to explain, go through the definition of redundant and non-redundant system. For redundant system, this is according to the DNV standard 119. For a mooring system to be defined as redundant, first of all, it has to be stable when it's losing one mooring line, and it has to meet the accidental load limit states criteria with 1 year event. And it is not the only criteria, even though it can meet the strength requirement with one failed mooring line. There should be no risk of collision with the adjacent structures. So it has to meet these two criteria for it to be called a redundant system. So when it's a redundant system, it's the lower consequence. So failing a mooring line is not going to cause a big issue. So it's a low consequence class. And for that, we are allowed to use lower safety factors on the load side, as shown on the right side. Is 135 for the mean tension and 175 for the dynamic tension. For a system to be called non-redundant, first of all, either it is not stable when the mooring line fails, or it doesn't meet the LS criteria, or when the mooring line fails, there's a risk of collision with other structure. Then it is classified as non-redundant. So either one of them happens, we cannot call it redundant anymore. So there's a high consequence for non-redundant system. Therefore, safety factors are higher. So you design the mooring lines with higher safety factors. In that case, you don't by design code you don't check any more failed mooring conditions anymore, because it is not allowed anymore. So you design the system stronger with the bigger lines, but then you don't worry about the failed mooring conditions anymore. Going back to the deep water, how our redundant system assumption for a three mooring line system, how it holds, and if there's any problem with those. So in a typical wind turbine, wind farm, the spacing in the wind dominant wind direction is usually 7 to 9 times the rotor diameter, and in the other direction it is 2 to 5 times the rotor diameter. For 15 megawatt turbine, the NREL's reference turbine has a rotor diameter of 240 meter, and 4 times the diameter, assuming 4 times the rotor diameter, it is about 1000 meters spacing. We can expect about 1000 meters spacing between the nearest floating foundations. For a three mooring line system, as shown on the picture left, with 3 mooring lines, when a mooring line fails and you lose all the restoring force from that mooring line, let's say on this picture from the south side, with a small event, small wind or wave and a current event, it doesn't have to be 1 year or 50-year event. You just need a little bit excitation on the foundation. You can have you can start to have big offsets. And even with small environment, you can have potential collision with the neighboring foundation. So for a tree mooring line system, when we look at our the nylon configuration with tree mooring line system, with failing one mooring line, as shown on this one, and giving a little bit of environment from this side, the offset can reach over 1,000 meters. So the collision with the neighboring foundation is quite possible, and in that case, power cable failure is also imminent. So for the same mooring configuration, if we add one more line and make it 4 mooring line, you can see the amount of offset decrease to around 340 meters, and what happens is it takes away the risk of collision with the neighboring structure, and we can still meet the consequence class 1. So if you want to use the consequence class 1 and and get rid of the risk of collision with the neighboring structure in deep water, we have to have 4 mooring line, and if you want to design it for a consequence class 1. So the summary for mooring design for deep waters: taut configurations with polyester and nylon, they both are feasible. That can both work. Use of nylon can reduce the mooring loads and therefore the anchor loads, and get smaller anchor design also. So that is the benefit of using nylon over polyester. However, the nylon hasn't been used as a long-term mooring in a long-term mooring solution yet, and but currently there are a few manufacturers that are going through the qualification process for the nylon, and S2H, we are part of one of the project, the demonstrator project that is going to be using nylon, and hopefully in a few years nylon will be qualified and will be an option for mooring solutions for floating offshore wind. In deep water, as opposed to shallow water, the mooring hang-off angle can become more significant and can amplify the mooring footprint. So we might have to stay with some certain limits. I guess the most important one is the DMV consequence class 1, which is a redundant system, may not be applicable for a 3 mooring line system for deep water floating foundation because of the large offsets experienced when a line fails. So there are two ways to mitigate that problem. One of them is addition of one more mooring line with a 4 mooring line configuration, and you can still use the consequence class 1 because of eliminating the risk of collision. Or we have to use it, if we are using 3 mooring line system, we have to use a consequence class 2 with higher factor of safeties. In addition, in deep water, based on the wind farm layout and the shared mooring lines and also shared anchors can be feasible, where they probably weren't feasible in the shallow water, but in the deep water they can be feasible. We can have, as seen on the animation to the right, we can start sharing the mooring lines and also the anchors, and a bigger cost saving will come from the smaller or less number of anchors. That will add up installation time as well, and additional saving is for the total mooring length, reduction in the total mooring lengths. For the power cable for deep water floating offshore wind turbines, again we are looking at the same 50-year environment. We are looking at a 66 kilowatt inter-array cable with three cores, and these are typical values compiled from few manufacturers. We look at the few manufacturer data, and these are representative values. And for two numbers that we need to focus on is the MBR, which is the bending radius. We don't want to go below 5 meter. That is our target. And the tension is a 500 kilonewton, so we don't want to go above 5 kilonewton, and we don't want to go less than 5 meter on the MBR in extreme in 50-year extreme events. Starting with a catenary option for deep water. Normally in shallow water, the catenary is not an option because of the bending radius at the touchdown. But in the deeper water, catenary power cable can be a feasible option. As you can see, it can meet the MBR limit. It is more than 5 meters, so it is not as severe. The problem is with the tension capacity. Right now, our inter-array cable has a 500 kilonewton tension, but we are seeing dynamic tension around 1000 kilonewton. So if the power cable had a higher tension capacity, this catenary option, power cable option, can be a feasible solution for deep water floating foundations. Alternatively, with the existing inter-array cable cross-section, we can make it work with a laser wave configuration. And with the laser wave, with the addition of buoyancy module, we can reduce the maximum tensions to 300 kilonewton, 310 kilonewton, and it also helps the MBR too. So this is a feasible solution for deep water floating wind using current available inter-array cables. But alternatively, for deep water, we are saying this is 1000 meter. We are assuming 1000 meter water depth. What the inter-array cable does is it comes down and it goes on the seabed, travels some distance, and goes up to the neighboring floating foundation. So in the deep water, does it really need to go to seabed? Can we suspend this inter-array cable between the two floating foundation and eliminate all the seabed contact and have some length reduction? Just one number that you should maybe I want to point out: assuming around 1500 meters spacing between two floating foundation, you would need about 3000 meters of inter-array cable to have it go all the way to the seabed and come back up to the floating foundation. So for when we start looking at suspending them between two foundations, first we did with no buoyancy, just suspend the cable as it is, and you can see the both the MBR limits and the dynamic tensions are exceeded quite significantly. So this is not really a recommended configuration, and all the dynamics of the power cable is amplified. So this the tension is quite high compared to even the catenary configuration. And the better option is having suspension with the help of buoyancy modules. And once we start using the buoyancy modules to reduce the tension, and it also dampens the dynamic motions too. So we have we have a configuration power. We can have a power cable configuration that can meet both the tension requirement and the MBR requirements with the suspended configuration. This is only viable in deep water, and I guess this is an opportunity. And as I was saying, this configuration requires about 1800 meter power cable length compared to 3000 meter in the previous slide. So that is around 40% reduction on length, on the dynamic cable length. And the dynamic cable is one of the expensive components in the floating offshore wind uh, systems, and in reduction 40% reduction in the length, and considering this is a wind farm with 40-50 turbines, that can add up quite significantly and can reduce the cost of energy. So to summarize the power cable portion, a simple catenary power cable configuration can work if the power cable tension limits are increased. We know that this may not be a big challenge because in the oil and gas industry, umbilical cables can go deeper, can go all the way to 10,000 feet deep. So there's solutions to strengthen the power cables. So it just hasn't been done yet. For this, so I think the manufacturer can accommodate that. Laser wave power cable configuration, as it is used in the shallow water, it can be used for deep water, and it can with existing power cable cross section, it can be feasible solution. And deep water brings the opportunity for inter-array cables, and they can be suspended between the floating foundations, and that can reduce the power cable length, reduce the cost, and also eliminate the seabed contact, and any auxiliary equipment that is needed on the seabed are eliminated. When we look at the suspended version, without the buoyancy option, just the catenary buoyancy, without the buoyancy suspension, currently is not feasible. It has to be more design optimization, more design iteration needs to be done if we really have to make that one work, but it is not recommended as first pass. And suspension with a buoyancy option, as it is currently stands as a feasible option. So this is, I think, the last slide on our webinar today, and if you want to take a few key takeaways today, and these are the bullet points for mooring and power cable. 3 things for mooring: for deep water floating foundations, taut moorings with polyester and nylon synthetic ropes are both feasible, and by eliminating the use of chain, that can have a positive effect on the levelized cost of energy and can reduce the cost of energy. And one important takeaway is the nylon versus polyester. Nylon behaves or reduces the forces on the mooring lines, and also therefore on the foundation, and also on the anchors, and so it has the advantages over nylon. But however, it can reduce higher offsets when compared to polyester. Mooring configuration with the minimum of 4 lines can be the minimum number of mooring lines. Instead of 3 lines, you might have to have 4 lines for deeper for deep water floating foundation because of the risk of collision. Or alternatively, when I use a 3 mooring line system, we have to use a higher consequence class and use a higher safety factors. For the power cable, the catenary and laser wave configurations are feasible. Just the catenary configuration will need power cable with higher tension capacities. Power cables can be suspended between the foundations, and which will eliminate the seabed contact and can significantly reduce the cable length, dynamic cable length requirements. Laser wave and the suspended laser wave configurations are feasible using the currently available power cables, inter-array power cables that are in the market right now. I think that is all I have, and now I do take your questions.
Great. Thank you so much, Yusuf. And thank you everyone for bearing with us with the rain and the wind in the background. We appreciate it. That's Houston weather. So we'll get started with some questions. Let me see. Okay, first one. Why do taut configurations with synthetic ropes are chosen over the catenary configurations?
Uh, the catenary configuration and semi-taut configuration, they rely on the chain weight on the seabed to have that the mooring restoring force. And naturally, you will need to have lots of chain laying on the seabed dormant. So that is additional cost on the chain. And the more chain you have, the more installation time you will have, and more maybe trips, offshore trips you will have to lay at all that chain, and chain takes lots of space on the installation vessels too. Whereas synthetic ropes, you can reel them, and eventually it will save you cost on the installation time and also the material cost. So that is the primary reason we believe using as much as synthetic ropes will be beneficial to the economics of the project.
Okay, great. Next question. Are the polyester ropes torque matched ropes or are they torque neutral ropes?
Actually, I have to look back and talk with the vendor to answer this question. I don't have answer to this question.
Okay, perfect. Yeah, and we can follow up with that person and talk more about that. Okay, next one. Have the required gripping/crushing loads on the cable to install in Deepwater been considered on the local cable design?
It has to be considered, but in our study we didn't go into that detail yet. Yeah, the clamps, I guess, needs to be designed accordingly to have that required surface area, but that we didn't go into that detail on the crushing of the power cable.
Okay, next question is, have you done any cost comparisons between the various mooring configurations?
We did, not on this study, but we did last year. We had an OTC paper. I think we can share that OTC paper. We had a cost comparison between catenary, semi-taut, and taut configuration using all chain system and the synthetic rope sections. Yeah, we had in last year at the OTC Offshore Technology Conference here in Houston. We have a study on that one, but not specifically for the deep water. It was more shallow water. But yeah, we did the cost comparison study. I would say, in the shallow water, the cost difference between the synthetic ropes and chain were not that dominant. But I think going with the deeper water, this separation costs separation differential between the chain system and the synthetic rope section will be more significant and dominant. In the shallow water, you still have to have some chain at the top and bottom. You have slight, like a short length of synthetic rope. So overall, it didn't have too much significance.
Okay, thank you. The next one, do you ever consider using floats or buoys intermittently spaced along the length of the mooring lines to reduce sag?
It came not on this particular study. For our system, for the taut system, there's not really much sag. This is a highly tensioned taut system, and the weight of the synthetic ropes are almost buoyant, so they don't have that weight for it to sag, let's say. But when we consider other mooring configuration, more looser system with more loose lines, we considered adding buoyancy modules. That was uh, not because of getting rid of the sag. It is mostly was at the bottom location where the chain is, and we don't want the synthetic rope, neither whether it is polyester or nylon, doesn't matter. We don't want to touch the seabed in a offset, let's say near side offset, where it gets looser and it gets slacker and can get close to the seabed. So if you want to avoid that, we we did put buoyancy modules on the chain or on the polyester section near the seabed, just to avoid the seabed contact, not because changing the mooring configuration and getting rid of the sag, which we don't see on the taut configuration with high preloads anyway.
Okay, thank you. Next one, what kind of anchor is used?
Anchors, okay, that's a good question. You know, I was saying we are eliminating the chain and we are looking at the taut configurations. One drawback of using taut configuration over the catenary configuration is the anchor type. Because for taut system, our anchor needs to be vertically, has capacity to resist the vertical loads, basically uplift force. And there are a few anchor types that can do that, which based on the seabed conditions, it can be suction piles if the seabed is clay and sand, I mean soil, or driven piles or drilled and grouted piles. Mostly these are the anchor types that are compatible with the taut mooring configuration, and they are on the expensive side of the anchors. And this on the catenary side, chain configuration, we won't have any uplift force, and we can use a smaller size and cheaper, let's say, anchors, drag embedded anchors. So we didn't design an anchor for this study, but it would have to be based on the seabed condition. It either have to be suction piles or driven or drilled and grouted piles, or alternatively maybe gravity, but usually gravity anchors are more expensive than the other three.
Okay, we'll keep going. So we've got a lot of questions today. Is there a difference in fatigue life between nylon and polyester?
There is not much guidance on the nylon fatigue life, actually. They are expected to be in the same range as the polyester. That's what we've been using actually, and they are the qualification program we are doing with the manufacturer right at the moment is focusing on doing the fatigue test also, and qualifying and getting the fatigue curves also. But the most important thing here is we have the chain in the system regardless, and the polyester and nylon they are going through the same tensions, and the chain fatigue life are usually in the order of 10, maybe even higher, lower than the polyester and nylon fatigue life. So our overall fatigue lives are governed by the chain fatigue life, not the synthetic rope polyester, not the synthetic rope fatigue lives.
Okay, thank you. How does the nonlinear behavior of the synthetic mooring lines affect the mooring?
That's a good question. The polyester, the nylon, especially the nylon, has very nonlinear stiffness profile, and it's documented in the testing and also in the design codes, ABS, DMV address that. And what happens is the nonlinear behavior of the nylon stiffness, it behaves like stiffer with the higher mean tensions. So it gets stiffer as the mean load goes higher, and it can act softer when the tension amplitude for a given mean tension is high. So it can act like a load reduction device as well with the high peak tension load. So once eliminating those that can eliminate some high peak tensions. You have more flexible mooring line, mooring component with a more uh, flexible stiffness properties in the system. You will have reduced peak loads. Once you have a reduced peak loads, that is pretty much you are designing your mooring line against dynamic amplitude. If you remember, the safety factors was 1.75 the amplitude. If you get rid of those peaks, that means you will have smaller design loads, and you can use uh, smaller size synthetic ropes. So it is very critical having a nonlinear stiffness correct in the system, and it helps for the case of nylon. It helps with the mooring design. It curbs some of the peak tensions, acting almost like a load reduction device itself.
Okay, great. I think we're going to squeeze in one more. Has the W power cable configuration been done before?
W power cable configuration, actually, it is not a new idea. It is used in the oil and gas industry, where umbilicals between nearby vessels can be connected like that. So it is field tested. It is done before, so it's not new. All the components, the bend stiffener and the buoyancy modules, and are all field proven, field tested, qualified components, and yeah, it is a mature concept, let's say.
Great. Well, thank you so much, Yusuf, for all the information on the topic. I know we have several more questions that we didn't have time to answer, but Yusuf will follow up with you directly if you answered a question. Sorry, if you asked a
Yeah.
question. And if you think of any more discussions you want to have, you can contact Yusuf directly using his details here. I want to say thank you to our audience for your time and participation. We hope you all found this useful and will join us for more webinars in this series happening monthly. You can check out 2H's LinkedIn page for more details and to sign up. And again, please look out for the recording of the webinar in your email in the next 24 hours. And we hope everyone enjoys the rest of their day. Thank you.
Thank you.